So folks, this video is a counterpart to another video that dealt with Green's theorem in circulation form. In this case, we're looking at Green's theorem in flux form, so I think it's really important that you identify that this is the flux video, not the circulation video, because the two will look really similar. So here are our goals. The first one is to define the divergence in 2D, then to give a visualization or visual interpretation of that divergence in 2D. We'll state Green's theorem in flux form, and then we'll work an example of Green's theorem in flux form. As before, you can go ahead and watch this in its entirety, or if you wish, I've included the timestamps so you can jump forward to the particular point in time that you want to watch the video for. So let's go ahead and look at the definition of divergence in 2D. So we're going to imagine that we've got a vector field f with component functions f and g. So the divergence at a point is given by partial f partial x plus partial g partial y. And that's usually how it's shown in shorthand notation. As a reminder, folks, in this course, there's a lot going on behind the scenes, and so sometimes we drop off some of the notation to make it easier to read. In reality, what we have when we talk about a vector valued function is a function that inputs a point, x comma y, and is going to output a vector at that, we can imagine at that point. So we give it by the two coordinate functions f and g. So we've got the function f of xy and the function g of xy, where f gives the x component of the vector and g gives the y component of the vector. And then the divergence is a pointwise definition, where we say the divergence of f at some point x comma y is given by partial f partial x evaluated at x comma y plus partial g partial y evaluated at x comma y. Or using another notation, we could say that's f sub x of x comma y plus g sub y of x comma y. So folks, I'm not really going to go into where we come up with this formula for divergence, although we're going to explore it in an example. However, if you'd like to learn more about the impetus for this divergence formula, I'll link a video here that you can go ahead and access. So my next goal is to give a visual interpretation of the divergence in 2D. I was hoping to go ahead and use the same example from last time, which was this vector field right here. But just out of curiosity, let's go ahead and actually compute the divergence of this. So the divergence of f in terms of xy, remember we said was, for 2D, partial f partial x plus partial g partial y. But if I take my component function, my first one, the f component function, and I take the partial derivative of that with respect to x, I get 0. Likewise, when I take partial g partial y, I also get 0. So this is not a good example to use because the divergence everywhere is 0. In fact, we would say that this particular field is source-free. Whenever the divergence is everywhere is 0, we say that the field is source-free. We'll get a better interpretation for that at the end of this exploration. So let's instead explore a few other vector fields. The first one I'd like to look at is f equal to 1 minus x, comma, 1 minus y. So I went ahead and graphed that vector field. Let's look at it. So let's go ahead and compute the divergence at a point right here in this vector field. I'll pick this point right here. And so let's call that point P1 maybe. So the first thing I'd like to do is let's actually look at how we gave the divergence as a statement, where we said the divergence of f at a point xy would be partial f partial x plus partial g partial y. Similar to what we saw when we analyzed circulation, let's go ahead and remind ourselves of a partial derivative with respect to x. We'll go ahead and look at a swath in the x direction, and we're going to ask ourselves, how are the x components of this function changing? Here's the x component of this vector, the x component of this vector, etc. What do we see in this case? As we move from left to right, partial f, partial y, or excuse me, partial f, partial x is less than 0. Why is that? Because those x components are getting shorter as we move from left to right. Likewise, if we look at the second statement in the expression for divergence, that's the partial derivative of something with respect to y. Let's go ahead and look at a swath in the y direction here. And let's look at the y components of each of these vectors. So what we see is as we move from bottom to top, the y components of these vectors are decreasing. That's what this is asking us about. So we have that partial g, partial y is also less than 0. In this case, we happen to be adding up the divergence and each of the two quantities is negative. And so we get that at point P1, the divergence of f is negative. Actually, the way I designed this vector field, any point you pick, the divergence will be negative in this. That is, you could do that same analysis at any other point, right here, for instance, P2, right here, for instance, P3. Of course, the pictures are a little bit harder at some of these other points. The reason why is because if we actually do the computation for the divergence of the entire field, we would have that the divergence of f at the point xy is simply, well, the partial derivative of the first component function with respect to x is -1, and we're going to add to that the partial derivative of the second component function with respect to y, which is -1, which gives us the divergence everywhere being -2. One way to interpret this is that in this entire region of this vector field, everywhere, every point is behaving in some sort of sense like a sink. By the way, there is a sink in this vector field, which is at this point right here, +1, 1. So hopefully this look at the partial derivatives helps to sort of explain what it means when you get a negative divergence or a positive divergence. What I'd like to do is give you another interpretation of this. So let's clear our work around point P1. And instead what I'd like to do is I'd actually like to put a small box, which we could think of as a closed curve, around point P1. So one way to look at this is that when we're computing the divergence, we are computing the infinitesimal flux at a given point. That is, if I were to compute the flux around this box for this curve here, remember that's running in a counterclockwise direction, the flux around here you would find to be negative. But if we kept shrinking that box smaller and smaller, that flux would still continue to be negative. And so we could talk about what we mean by the infinitesimal flux at a point, which is the same thing as the divergence at that point. If you're interested in a better explanation of that, see the video that I've linked below. But once we think of this in terms of an infinitesimal flux at a point, then one way to interpret what's happening here is that when we look at this box that I've drawn around P1, or any smaller box for that matter, more vectors are going in than are going out. That is, if you were to sum up all of the vectors going in, their magnitudes, and look at all the vectors leaving the box, going across the boundary, we would see that more is going in than's going out. Because of that, we would say that point P1 behaves like a sink. But there's nothing special about our point P1, and you could have computed that at any other point in this vector field, because everywhere, we've said, the divergence is the same as -2 at -2. Let's look at another example. So now I want to look at the vector field f is equal to, this is similar to the one before, x minus 1, comma y minus 1. Before I graph it, let's take a guess at what we should expect to see for the behavior of this function, for the behavior of this vector field. So if we go ahead and take the divergence of this vector field, the divergence at any point is simply going to be, well, it is the partial derivative of f with respect to x plus the partial derivative of g with respect to y. Taking these partials, we get 1 plus 1. That is, the partial derivative of x minus 1 was 1, and the partial derivative of y minus 1 was 1. So everywhere the divergence here is going to be 2. So we expect every point, since it doesn't matter which point we plug in, the divergence is always 2, we expect every point to be in some way behaving like a source. Let's now look at the vector field. So here I've sketched this vector field, and sure enough, if we go to any point right here, P1, if we look at what's happening as we take a swath in either the x direction or in the y direction, we can go ahead and look at how the magnitudes of the components, the respective components, are changing as we either move from left to right or top to bottom. So that's one way to see that the divergence there would be a positive quantity. We see that because, for instance, the x components around P are becoming less negative, which tells us partial f, partial x is positive. Likewise, if we look at the y components around P, we see that those y components are becoming less negative, which tells us that partial g, partial y is positive. And so the sum of those two positive quantities is again positive. But perhaps the better interpretation to see what's going on around point P is to instead think about putting an infinitesimally small box around point P. For purposes of illustration, though, I'll make it a little bit bigger than that. And what we can see is that if we measure the flux around this box, let's orient it with a direction, as we go counterclockwise, we see that if you sum up the components of the vectors that are normal to our direction of travel, we see that we have more of the components are heading in the direction of our normal vectors outwards than are inwards. So for example, here I have this normal vector here, and we would have a little bit of the force function heading into the box, but that's a very small quantity. If we were to take that dot product would only be about yay big. Whereas over here, when we look at this force vector, or this vector in our vector field compared to this normal vector, and we take their dot product, we have quite a bit of that in alignment there. So we'd be adding up, this would be greatly counterbalancing this. And that would be true as you go the whole way around. So that's another way to see that, you know, if you put an infinitesimally thin box around that point P1, that infinitesimally thin box would correspond to having a positive flux, which corresponds to that point saying at that point we have a positive divergence. So let's quickly look at two more examples of this. So here I have two more vector fields that I want to look at, and we can talk about the divergence on these. We won't do the calculation, we'll just look at the picture. If I were to think about an infinitesimally thin box around this point, again I've drawn it much bigger so we can see, we would say that the net flux around this box is positive, so the divergence at that point is positive. Again, if you'd rather do an analysis looking at partial f, partial x at that point, plus partial g, partial y, well, first of all, partial g, partial y is always 0, and you would see that partial f, partial x is positive. That is, as we move from left to right through a swath through that point, the x components of those vectors are getting larger, so it's increasing. Over here, though, we would see the divergence at this point is 0. So again, the divergence at P1 is positive, whereas the divergence here at P2 is negative. Contrast that with this other example where I've given the vector field 1, 0. Notice that all throughout here, if I were to think about an infinitely thin box at around this point P1, again I've drawn it bigger so we can imagine it, but the flux around that box would be 0. That is, if we sketch some normal vectors along this box, sure, there would be a positive flux as we traverse this first path, but that would be counterbalanced exactly by the negative flux as we traverse this path. And of course, as we pass through either the upper or the lower curves, we see that the dot product between the normal vectors and the force vectors, the vectors in the vector field, would be 0. So this has a divergence of 0. Again, if you'd rather look at the pointwise way of looking at that, where you actually go through and you look at partial f, partial x, plus partial g, partial y, first of all, again, there are no y components. The derivative of 0 is 0, but so is the derivative of the x component function f. That's also 0. And so we can see that as we go from left to right, if we take a swath through there, the x components aren't changing, and as we take a swath through there, the y components aren't changing, so the divergence at that point is 0. So I'll conclude with a more complicated example. Here I've got a vector field x squared y comma y squared, and I've gone ahead and computed the divergence already, taking the partial derivative of the first component function with respect to x to give me 2xy, and taking the partial derivative of the second component function y squared to give me 2y, and I went ahead and put this in factored form. The first thing I would say is that I think that for some of these regions you might be able to immediately identify the divergence, but some of these other regions it would be quite difficult to figure out what the divergence is. So unlike the carefully chosen examples from before, I would caution you from trying to figure out what the divergence is of a vector field just by looking at a point, but rather the correct way to do it is to do this calculation of a divergence and then evaluate it at a particular point. That will tell you whether the point is behaving as a sink or as a source. So what I'd like to do here is just quickly talk about the divergence in different portions of this graph. We see here that the divergence will be 0 when y is equal to 0, or if x equals -1. So just for fun, let's go ahead and divide this graph up into those regions. Here's where x is equal to -1, and here is where y is equal to 0. So let's go ahead and, now that we've divided this up into regions separated by where the divergence is 0, let's calculate the divergence at a few points. So let's go ahead and calculate the divergence of f at the ordered pair 0, 1. So if we go to plug that into the calculation, the simplified version of the divergence, we would have 2 times 1 times the quantity 0 plus 1, which gives us a divergence of 2 at the point 0, 1. So at the point 0, 1, we found that the divergence here was greater than 0, so that means that at that point it's behaving as a source. Now again, I don't think that you could do that trick of drawing an infinitesimally small square around that point and determining the divergence at that point. Although for a point maybe over here, you would be able to see that that point is behaving more as a source than a sink, because there's a net positive flux over that small square that I've drawn. Likewise, we could take another test point, say the test point down here at 0, -1, and if we compute the divergence of f there, well, we're simply going to get -2. Again, I don't think that it's clear that the divergence is less than 0 at that point. I don't think you can draw a small square there and see that it's behaving more as a sink than a source. Although if you went further afield for this point right here, you could see that the net flux across this square appears to be negative. That is, more of the vectors are pointing inwards in comparison to our normal vectors around the path than pointing outwards. So I'll leave you to go ahead and test the other two regions. You could go ahead and take, for example, test points -2, 1 and -2, -1 and compute the divergence there and determine whether in those regions the vector field around a point is behaving more as a sink or a source. So I'll let you take a look at that. So folks, we'll return to this initial example. And we said initially we did the calculation to find that the divergence everywhere in this field is 0. We said that that was source free, so it was an interpretation of that, meaning there's no point that's behaving as a sink or behaving as a source anywhere in this vector field. Again though, I don't think you can always determine that just from a visual inspection here. Maybe you can see that there's nothing behaving like a source, but maybe not. Maybe you might think that that looks a little bit like a source to you, or maybe right here might be behaving a little bit like a source. And you can't just look at these visually. You do have to do the divergence calculation. However, if you do want to fall back on some visual examples, take a look at the first few examples that I gave you in this demonstration. This concludes our methods for interpreting the divergence of a vector field in 2D. And now we'll move into Green's theorem for divergence and flux. So folks, the next thing we want to do is state Green's theorem in flux form. So let's go ahead and load the info for that. So the conditions for Green's theorem in flux form are identical to the conditions for Green's theorem in circulation form. So again, we're going to have a closed, simple, piecewise smooth curve oriented counterclockwise, and we're going to think of that as serving as the boundary for some region. So that curve C is the boundary of this region R here, where R is connected and simply connected. So we've now talked about two different ideas, and they are related to one another. The first idea is the notion of flux, which asks the question, if I look at some unit normal vectors around this curve, remember we orient the normal vectors outwards based on the direction of motion, that if I were to take and look at whatever the vector function is, the vector field f, that's our vector field, where it has these continuous component functions with continuous partial derivatives. If I were to add up, and these f's don't need to be all going the same way. If I were to add up the dot product of each of these blue vectors with each of these black normal vectors, those dot products, that gives me a small quantity that tells me to what degree, is the force, the vector in the vector field in alignment with the normal vector. In this case, this is opposite alignment. We've got a little bit of opposite there, a little bit of opposite there. Here they're in alignment with one another, so the dot product, when I dot the black normal vector with the blue force vector, we've got a positive component of that. If I add up all of those red components there, that gives me the flux across this boundary. So the flux across this boundary is the closed loop integral, and we wrote flux as f dot in ds. So again, that's the normal component being dotted with the force, with the vector field. Green's theorem says, rather than doing that, what we could do it instead is look at all of the points on the interior here. And at each one of those points, we could calculate the divergence at those points. That is, we'll ask the question, is that point behaving like a sink or like a source? And so Green's theorem says that computing the flux across the boundary is equivalent to computing the to adding up the divergence at all the points on the interior of R. So there's our statement of the divergence, df dx plus dg dx. So that these two calculations are equivalent. And that means that sometimes when we have a double integral of this form, it may be more convenient to parameterize a curve around the region and evaluate this integral. Likewise, if we are dealing with a line integral, a closed loop line integral in a vector field, it may be more convenient, and we're looking at the flux on that line integral, it may be more convenient to compute the double integral, which everywhere adds up the divergence. So that's what Green's theorem says. Let's go ahead and put it into practice in the next example. Let's go ahead and work an example that will allow us to check Green's theorem. We're going to verify it. And we'll also explore some of the other topics that we've been looking at in this video. So here we've got a vector field that's permeating our space. So at every single point in the xy plane, we place a vector. But we're going to restrict our focus to a particular region R of that xy plane. In this case, our region R is going to be the unit disk. And the boundary of the unit disk will just be the unit circle. Let's go ahead and sketch that quickly. So here we've got our region R, which includes everything I've drawn. But if we want to restrict our attention to just the boundary, we would have this curve here, C, which is our boundary. Because we're going to be computing, even though we state flux, we're going to be computing what we mean by outward flux. We need to make sure we have the correct orientation. So let's assign an orientation there. So now the first thing we're asked to do is to go ahead and compute the two-dimensional divergence of this vector field. Remember, that has nothing to do with our region R here. It has everything to do with the vector field that describes the space that this region R sits inside of. So if we want to compute the divergence of F, that's a point-wise calculation where at every single point we will talk about how that point behaves instantaneously, like a source or like a sink. And our definition then that measures that is the partial f partial x plus partial f partial y. And in this case, our function f of x is the first coordinate, f of xy is that first coordinate function, and our function g of xy is that second coordinate function. So we get the divergence will be 2x, that's that partial, plus 0, that's that partial. So our divergence is 2x. Notice this is saying that the divergence will be positive if the x-coordinate is positive. Meaning, if the graph is to the, or if the point is to the right of the y-axis, that point will behave as if it were a source. Likewise, if the x-coordinate is negative, meaning we are to the left of the y-axis, then the point will behave as if it were a sink. Finally, if the x-coordinate is 0, if we're along the y-axis, then that point will behave as neither a sink nor source. So folks, there's no reason to sketch this vector field, but I went ahead and did so for us, so let's look at that. So here's our vector field F, which is the blue vectors that I've sketched. And we can see that as our x and y coordinates move further away from the origin, those vectors become longer. And the closer we are to the origin, the smaller those vectors become. So just to clarify what we mean when we check the divergence at a few points, if I were to check the divergence, say, right here, the vectors coming into this instantaneous or infinitesimally small cube are shorter than the vectors leaving it. Meaning that at that point, it's behaving as if it were an instantaneous source. Likewise, if we look, say, down here, we have that the vectors coming in at that point are longer than the vectors that are leaving that point. Meaning that this point right here, where we are to the left of the y-axis, is behaving as a sink. So although we didn't need to look at the vector field to determine the divergence, it gives us a nice confirmation that this formula for the divergence matches the vector field that we see by inspection. The next thing we're asked to do is to compute Green's theorem, both directions. So let's first look at the flux form that we want to compute. So the flux integral for this is that's the closed loop integral of the vector field f, and we're going to dot that with the normal vector of our curve, ds, where c is this unit circle oriented clockwise. So this is our flux integral, although this is not very easy to work with the calculation. So another way to give this integral is to say that that is this integral here. So this would be f dy minus g dx. That's another way to give the flux integral. To clarify, once we've got a parameterization, of our curve C. So in this, once we've got a parameterization, we can actually evaluate this line integral as if it were an ordinary integral. Or if we like, we could pull the dt's completely out. So double check that all I've done here is parameterize the first vector function, the first coordinate function, with x of t and y of t, the second vector function with x of t and y of t, and I've replaced dy with y prime of t dt, and I've replaced dx with x prime of t dt. So everything's under the parameterization, including our limits of integration. So now we just need to give our parameterization of our boundary curve, C, and in this case, since our region is the unit disk and our boundary is that green unit circle there, our parameterization of the curve, or a parameterization that we could use, is r of t is equal to 1 cosine of t, 1 sine of t on the interval from 0 less than or equal to t less than or equal to 2 pi. Folks, many other parameterizations would work for this particular curve. However, for the parameterization to be valid, it has to retain the original orientation of the curve. So our parameterization starts us at this point right here, and we continue in a counterclockwise manner until we return to that point. Any other parameterization of that unit circle would work, but it must travel in a counterclockwise manner. So now that we've got our parameterization, computing the flux integral is simply a matter of plugging and chugging. So we've got the ordinary integral from t equals 0 to t equals 2 pi. Then I'm going to take the x component of our vector field and subject it to our parameterization. So that will be cosine squared of t plus sine squared of t. That is our f of x of t, y of t. And we're going to dot that with y prime, or multiply that by y prime of t, which is our derivative of the first component function, which is the cosine of t. Then we're going to subtract from that the function g parameterized, but in this case the second coordinate function, g of t, is just identically 0. So even though we've parameterized our curve, this component is still 0. And just for completion's sake, we're going to multiply that by x prime of t. That's the derivative of our x coordinate function for our parameterization. So I'm going to multiply that by the derivative of 1 cosine t, which is minus the sine of t. All of this is then integrated with respect to t. In this case, things clean up very nicely and simplify. We get the integral from 0 to 2 pi. The expressions cosine squared t plus sine squared t by identity is 1. So we just get the cosine of t dt. Evaluating this gives me the sine of t evaluated from 0 to 2 pi, which is just 0. Folks, although we don't need to look at the picture, let's go ahead and do so and verify what we just saw. So what we've just done in our flux calculation is we said, hey, at every single point along our unit circle here, we're going to give the outward-facing normal vector to that curve. Further, at every single one of those points, we're going to dot that normal vector with the vector in the vector field. So you can see that right here we have a small, this would be infinitesimally small positive flux, because when you take the dot product of the green and the blue vectors, you get a small positive component. Likewise up here. But notice that, for instance, this particular normal vector on this side of the circle, diametrically to the other side, we would have a similar normal vector, and we would have a similar vector field vector, but pointing in the opposite direction. And when we take this dot product, we get a small negative component for that infinitesimal flux at that point, and this will counterbalance this. For that reason, there is no net flux as we travel around the entire circle, although if we were to travel just one component of it, we would have a positive flux, or maybe this component, we'd have a negative flux. But the net flux as we start from one point and return to it is 0. And that's what we saw in our flux calculation. So again, we computed the flux over our curve, and we found it to be 0. What we're doing here, though, is we're verifying Green's theorem, which says rather than having calculated the flux, we could have also calculated the divergence over the interior. So the second integral in this statement of Green's theorem is that if we go to calculate the divergence of f over the interior, we should get the same expression. In part A, we calculated the divergence, and we found that to be 2x. Just to verify, we took the divergence through this calculation here and found it to be 2x. So now we just need to evaluate this double integral. In this case, I think it makes most sense to think about r in terms of polar coordinates because it is the unit disk. So our r is the set of r theta such that, and then our r values go between 0 and 1, and our theta values go between 0 and 2 pi. So then going ahead and performing the standard polar substitutions, this would be the integral from theta equals 0 to 2 pi, and r equals 0 to 1. And then we have for an integrand 2, and then under the transformation, r cosine theta, that's our integrand. And then the area component is r dr d theta. So there's our dA right here. There's our integrand here, and we're now evaluating the equivalent iterated integral. So this is the integral from 0 to 2 pi of the integral from 0 to 1 of 2r squared cosine theta dr d theta, and I'll just evaluate this. So notice in evaluating this integral, we also got 0, although we arrived at that integral, that value, through different calculations. So let's go ahead and explore this in the image from the context of not flux, but divergence. So rather than looking at the flux across the boundary, what we're doing instead is we're looking at the divergence in the interior. Notice we already put up here that this particular point right here, and imagine this box to be infinitesimally small, this particular point right here has a negative divergence because it's acting as a sink, meaning these vectors are, we've got longer vectors coming in than we have coming out. So right here, we've got a small sink. But this is perfectly balanced out by this point right here, where if we looked at the infinitesimal divergence right here, we would have longer vectors coming out. That's maybe a little bit exaggerated, but we'd have longer vectors coming out and shorter vectors going in. So this point right here is behaving as a source. And so we could see roughly that for all points in this quadrant, maybe, or in fact all points in this half plane, they are counterbalanced out by the points in this half plane, which gives us a net divergence over the entire region of 0, even though the divergence at individual points is not necessarily 0. So what we've done is we've verified Green's theorem, which states that we could either calculate the flux integral across the boundary of our region, or we could compute the divergence integral across the interior of that region. And in either case, we get the same quantity. Just to complete this out, remember that we said that the entire region isn't source-free. There are places where the divergence is non-zero, so the vector field is not source-free. Folks, I hope this video was helpful. Let me know if you have any questions.